Hello everyone, welcome back to mychemcorner. So in this video we are going to learn portions related to class 12 or second PUC chemistry. We're starting with the very first chapter from physical chemistry, which is solid state. So in this video we are going to cover only a few topics, and I'll be doing this particular chapter in bits, so the video is not long. So in this particular video I will be doing from the classification of solids, classification of crystalline solids will be going in detail, and will also be giving you some examples related to it. And in the end, I will also be giving a difference table which will try to conclude the entire topic that we're going to talk in today's video. The remaining part of the topic will be there in other videos, so please stay connected. So in this video, we will be starting with the introduction, which is we're going to talk about the characteristic properties of solid. So since we're talking only about solid state, we're only going to restrict our entire explanation only to solids. So as we know, in solids, when you look at the way the atoms are arranged in a solid, they're very much close to each other. So when they're close to each other, the main reason of this is because they have strong intermolecular force of attraction. Then when you have strong intermolecular forces of attraction, which means they are very close to each other, basically they have a very short intermolecular distance. Basically, when you take two different atoms in the same solid, their space in between them, or the intermolecular distance, is very short. They have a fixed position for consistent particles. Now if you see how these atoms are placed in a solid, they have fixed position. They don't change their positions. Now when you look at how they are placed in the solids and what sort of motion they have only vibrational motion, because they basically cannot move. They have a very short intermolecular distance. The force of attraction between any two atoms in a solid is very strong. So because of that, they cannot move. There is no other motion in the solid. They can only have vibration about their same position. Now because of all this, they have a definite mass, a definite size, and a shape. And here solids are rigid, they are incompressible, which means when you try to take a solid and you try to compress them, it's not possible to compress a solid. It's only because of all these points. Their intermolecular force of attraction is very strong. So because of that, they are incompressible, and they also have a high density. So that was about a small introduction on solids. Now from here, let's move on to classification of solids. So when we do practicals also, we have learnt about this particular classification in grade 11 or in first PUC. Whenever we give you salt for salt analysis, your teachers would have told you, when you look at the salt, what do you see? Right? Or when you take a pinch of a salt, what do you see? You can feel some crystals in them, and sometimes they are like talcum powder, very smooth, very soft. So we're going to base them on those two natures itself. We have two types of solids. One is crystalline and the other one is amorphous. You will have come across these terms again in practicals. So if you have, say, crystals, when you take a pinch of the salt and you can feel crystals, such kind of solids are called as crystalline solids. Then the other type of solids, when you take a pinch of it, it may feel like talcum powder that you apply on face, or like chalk powder. Such kind of solids come under amorphous solids. So let's look at the characteristic features of each of these type of solids. Now if you look at crystalline solids, they have an orderly arrangement of constituent particles. And that is why crystalline solids have a definite geometry. Whereas if you look at amorphous solids, they do not have an orderly arrangement, therefore they don't have a regular shape. That's why amorphous solids are more powdery, they don't have a consistent arrangement of particles. That's why they appear powdery and they're very soft. Then crystalline solids possess short range and long range order, whereas amorphous solids possess only short range order. Let me explain you what the short range or a long range order is. Now if you're looking at short range and long range order, I have taken arrangement of crystals here. So basically this is a crystal, and in this I have small spheres which are placed next to each other. Same thing over here. Now in this case, if you see, you have an orderly arrangement, which means I have a yellow sphere and then I have a green sphere and then I have a yellow. So basically I'm having alternate yellow green spheres. So here if you see, when these neighboring particles are joined, if I'm trying to join these four here, I'm going to get a geometrical pattern. Right? And when I try to look at the entire crystal, I'm getting the same pattern repeated again. So if I try to join the next set of square, I'm still getting the same pattern. If I had a next one, I'm going to get the same. So when I keep joining, I'm going to get a regular pattern, a regular geometrical pattern over a long distance. So this type of a pattern where I can get a regular method or over a short distance or over a long distance, this type of an arrangement is seen only in a crystalline solid. Alright, so if I'm looking of the same type of an arrangement in amorphous solid, here if I look at the arrangement of these spheres, I have a yellow sphere, then I have a green sphere, I have a yellow sphere, and then I'm having yellow again. So if you see here, the pattern of arrangement is very irregular. It's a very random arrangement. Similarly, when I go down, when I have a yellow sphere, then the remaining all three are green spheres. So there's a very irregular arrangement of pattern. But over a short range, which means here, I have a yellow sphere, I have a green sphere, yellow and a green. So when I try to join the centers of these spheres, I'm getting a regular pattern. But that's not continued throughout the entire crystal. So which means here, this particular arrangement is seen only over a short range. And this type is seen only in amorphous solids. So basically in a crystalline solids, you will see both short range and a long range order. Whereas in amorphous solids, you will only see short range order. So basically you're talking about the arrangement of particle over a regular pattern, either over a short range or a long range. That's what your short range order or a long range order in a crystalline or an amorphous solid mean. Now, the next point of difference between both are crystalline solids have a very sharp melting point. They have a very defined geometry. They have a very consistent arrangement of particle. So when a melting point is done, they will give a very sharp melting point, a single value for a melting point. Whereas if I'm looking at the amorphous solid, melting point is going to be over a range of temperature only because they have a short range order. They have a very consistent arrangement of particle only for a small range, and then there's a variation again. So what happens is when you try to do a melting point, it's going to give you over a range of temperatures. Then the next one is anisotropic. So crystalline solids are said to be anisotropic, which means say I want to measure some physical quantity. For example, I want to measure a refractive index of a particular crystalline solid. Now when I try to measure them in different directions, it's going to give me a different value. That is what anisotropy means. Now when I look at amorphous solid, it is going to be isotropy. So say for example, in this case I want to try to measure a physical quantity which is velocity of light. So when I look at amorphous solids, they're isotropy, which means the physical quantity that's measured in an amorphous solid will give me all identical value no matter in what direction I measure them. So basically crystalline solids are anisotropy, which means they will give different values in different directions. Isotropy for amorphous solids meaning they will give the same value in all directions. All these are only based on how the particles are arranged in that particular solid. Now the next one is, say I'm taking a crystalline solid and I want to cut it. Now because they have a consistent arrangement of particles, they have both short and long range order. No matter how I cut it, it's going to give me a smooth surface. But the same thing when I do it with an amorphous solid, it's going to give me irregular surface because there is no orderly arrangement of particle at all. So when I cut it, it's going to give me an irregular pattern. Then we're going to talk about definite value for enthalpy of fusion. So what is the meaning of this enthalpy of fusion? Let's break the term. Enthalpy basically means energy. So here, how much of energy change is required when you're trying to heat a solid? So when you do all this process, it's going to give you a definite value for a crystalline solid. Again, you get a definite value for a crystalline solid because there is orderly arrangement of constituent particle. But the same thing when I see for amorphous solid, they don't have a definite value for enthalpy of fusion because there is no orderly arrangement. So enthalpy of fusion is nothing but heat of fusion. It means it is a change in its enthalpy that is caused due to heat. That is the meaning of enthalpy of fusion. Then the next difference is crystalline solids are true solids. They have proper pattern of arrangement of constituent particles over a long range, over a short range. They have a very sharp melting point. When you try to cut them, they have smooth surfaces, therefore they are true solids. But if you look at amorphous solids, they are pseudo solids. It's because of all these points where they show no correct orderly arrangement of the particles. They possess only short range and they melt over a range of temperature. So these are few classifications, two classifications solid and differences between crystalline and amorphous solid. Now this particular point is very important for exam point of view. They can ask for 3 marks. Give any 3 differences between crystalline and amorphous solids. So that's an important topic for exam point of view. Now that we've learned about the classification of solids, we will move into classification of crystalline solids. So we learned 2 classifications of solid, amorphous and crystalline. Now we are going to learn classification of crystalline solids. So here we have 4 types of classifications of crystalline solids depending on bonding. We have ionic solids, we have covalent or network solids, we have metallic solids, and we have molecular solids. So here when you look at ionic solid, you can just take a simple example of an ionic salt like sodium chloride, basically talking about its ionic bonding. Then talking about covalent bonding, you would have learned in first PUC. Diamonds have covalent bonding, so you can take an example of that. Metallic solids, you can take any metal in which you can have a metallic bonding. Sodium, potassium, any metal can be considered. Molecular solids, we will go into detail later because we have certain classifications under molecular solids. So examples will be in detail for that. So we will go into that later. So here let's go into in detail for each of this, looking into its characteristic features and certain examples. So here, ionic solids. Now if you look at ionic solids, as the name says, the constituent particles are going to be ions. So here we have 2 types of ions. One is cation and the other one is anion. So if you look at this picture here given below, it's basically a crystal lattice of sodium chloride. So you have one cube here and then another cube behind, another cube here and another cube here. So basically we have 2 layers of cubes placed like this, giving you a crystal lattice of sodium chloride. Now what are these spheres here? The bigger green spheres that you see are chloride ion and the smaller spheres that you see are sodium ions. So these are constituent particles of an ionic solid, and how are they held? They are held by strong electrostatic force of attraction. Now, here, because the bonding is really strong, they are hard, they are brittle, and they have high melting and boiling points. It's not really easy to get a melting or a boiling point at a low temperature for an ionic solid. You need to heat at a much higher temperature. Then, when these are present in solid state, basically like a salt, they don't conduct electricity because these ions are not free to move. But the same thing when you try to melt them or you try to dissolve them in water, these ions will become free. Sodium ions will be free, chloride ions will be free. Therefore, they will start conducting electricity. Now, classic examples of these are sodium chloride, zinc sulfide, magnesium oxide. These are some of the examples of ionic solids that you can give. Now, the next one is covalent or network solids. For this, the example that you will look at is diamond. We know that diamond has only carbon and the bonding between them is covalent bonding. They're very strong. So here the constituent particles are covalently bonded non-metallic atoms. If you look at diamond, diamond has only carbon. Carbon is a non-metallic atom. So here the bonding between them is covalent. Between what? Between non-metallic atoms which will extend in a 3-dimension. So because they are extended in 3-dimension, they will be also called as giant molecules. Covalent bonds are strongly held at lattice points. It's not really easy to break diamond. Why? Because they have very strong covalent bonds. Because of that, they are hard, they are brittle and have extremely high melting point, higher than ionic solids. Now, in this case, in case of your covalent solids or network solids, they don't have ions or they don't have free electrons. Because of all this, they don't conduct electricity, therefore they are called as insulators. Insulators don't conduct electricity. They don't have free electrons. They don't have free ions. So they are called as insulators. But out of all these, you have an exception called graphite, which we had learnt in first PUC or class 11 in detail. Example of this is diamond and quartz. Now the next one is metallic solids. Now metallic solids, you can just take any metal like sodium, potassium, lithium, any metal. So the constituent particle in a metal is basically a positively charged ion, a cation, and sea of free electrons held by metallic bonding. Metals have a tendency to lose electrons, so obviously those electrons are free. And these electrons are held by metallic bond. Now, since the strength of metallic bonds will vary, it depends on the property of each metal. The metallic bonding is also going to vary in strength. Now, based on the strength of the metallic bonding, their melting points are also going to vary. Now, we all know that metals have a very characteristic feature of being highly malleable and ductile, which means you can beat them to thin sheets or you can draw them to thin wires. Both properties are possible in solids. So they are highly malleable and ductile. Now in metals, because they have a tendency to lose electrons, there are presence of free electrons. Therefore, they have very high electrical and thermal conductivities, and that's why you have metal wiring in electrical equipments and all of that. It's because of these free electrons that will help in conduction of electricity and will also help in thermal conductivity. So classic example you can give of any metal, sodium, zinc, copper, any metal can be given. Now the next one or the last classification is molecular solids. Molecular solids are basically soft. They have a very low melting point. These will tend to exist in liquid. They are in the gas state at room temperature and pressure. And these are non-conductors of electricity. They don't conduct electricity at all. Now, based on the nature of their binding forces, molecular solids can be classified as 3 types: non-polar solids, polar solids, and hydrogen bonded molecular solids. So, there are 3 types of molecular solids that you can classify: non-polar, polar, and hydrogen bonded. So examples under each of these category will be solid iodine. They are non-polar. Solid HCl, which is polar because you have two poles, a positive pole and a negative pole. Hydrogen bonded is ice, basically water. Right? When you try to freeze water, the water molecules are bonded to each other because of strong hydrogen bonding. So let's go in detail for each of these classifications. So first one, you have non-polar molecular solids. Now under this, the constituent particles are atoms or molecules which are held by weak London forces. That is for non-polar molecular solids. Example is solid iodine. If you are looking at polar molecular solids, you want to form a molecule which is polar. So basically here the constituent particles are molecules which are held by dipole-dipole interaction. Basically a positive pole and a negative pole. So example will be solid HCl. And the last one is hydrogen bonded. So of course here constituent particles are going to be molecule. Their forces that are holding them together is very strong hydrogen bonds. Example is going to be ice. So these are a few points which are talking about differences between non-polar, polar and hydrogen bonded molecular solids. So these are few classifications of solid and further classification of crystalline solids that we've learned along with example. So I have a table here. Now in this table we are going to fill this up with whatever information we have learned right now to just sum up or to conclude the entire video. So let's see how to do that. So here in this table, let's fill in for the type of solid, the first one being ionic solids. Its constituent particles here are going to be cations and anions. The binding force here is electrostatic force of attraction. The physical nature here was hard and brittle. Electrical conductivity in this case, they were insulators in solid state and conducts electricity in molten state. Melting point here was very high. The example for this can be sodium chloride. Now the next one here is for type of solids. We have covalent solids. In this case, the constituent particles were non-metallic atoms. The binding force in this was covalent bonding. Physical nature here was hard and soft in case of graphite, which is an exception. The electrical conductivity here was in case of compounds like diamonds, they were insulators. But when you had a graphite as an example, which is an exception, they were conductors. That's only because in graphite we have benzene ring where there's delocalization of electron. Because of delocalization of electron, they conduct electricity. Melting point here is very high because of covalent bonding. Example that you can give is diamond. Now the next one here is metallic solids. Under metallic solids, you will have only cations or positively charged ions. The type of bonding is a metallic bonding. Physical nature here is that they are hard, malleable and ductile. Electrical conductivity, they will conduct electricity. Melting point here is fairly high. And an example for this, you can give any metal. Now the next one is for molecular solids. Under molecular solids, we learned non-polar molecular solid. Now the non-polar molecular solid, we have atoms as constituent particles. The binding force here was London forces. Physical nature for this, it was soft. Electrical conductivity, it was acting as an insulator. Melting point in this case is very low. An example for this is solid I2. Then we have the next classification, which is polar molecular solids. Under this, the constituent particle is a molecule. The binding force in this case is dipole interaction. The physical nature of this is soft. This will act as an insulator. The melting point here is low. And an example for this is HCl. And the last classification is hydrogen bonded molecular solid. In this case, the constituent particle is a molecule. The binding force in this case is hydrogen bonding. Here, physical nature of this is hard because the hydrogen bonding is very strong. Electrical conductivity, again, it's an insulator. Its melting point is low. And an example for this is ice. So this is basically what we've summed up through the entire video in a single table. I hope this table will be helpful for you all once you actually learn the concept in the previous the previous part of the video, and then move into the table, and then it's going to be easy for you all. So the remaining part of the chapter will be done in the following videos, so please stay connected. And if you have any further recommendations or a particular topic that you want me to do, please don't hesitate to put a comment in the comment box. Or if you have any other queries related to other things, please don't hesitate to send me an email to the email ID given in the description box below. I'll see you in my next video. Thank you so much for watching.